The Big Bang didn't happen anywhere. That fact destroys how you picture the universe's birth. You're imagining it wrong right now. The moment you think explosion in space, you've missed the point completely. Tonight we're discovering why asking where makes no sense, and why your mind can't grasp what really happened. Before we dive into this cosmic mystery, drop a comment about where you're listening from. If you enjoy these mind-bending journeys, consider subscribing. These explorations are meant to be shared. Picture a massive bomb exploding in dark, empty space. Debris flying outward in all directions. That's how most people imagine the Big Bang. That mental image is completely wrong. The Big Bang wasn't an explosion that happened somewhere. It was the birth of somewhere itself. Before this moment, space didn't exist. Time didn't exist either. There was no empty room for anything to explode inside. Think of it this way. Every explosion you've ever seen needs a place to happen. A bomb explodes in air. Fireworks explode in the sky. But the Big Bang created the very concept of place itself. A scientist named Hubble proved this in the 1920s. He measured how fast distant star groups move away from us. What he discovered changed everything. These star groups weren't flying through space like explosion debris. Space itself was stretching and carrying them along for the ride. Right now, as you listen to these words, space grows larger between distant star groups. The universe creates new space constantly. This stretching of space is what we call the Big Bang. Not an explosion in space, but the birth of space itself. Right now, you're standing at the center of everything you can see in the universe. So is every other person on every other planet scattered across space. This sounds impossible, but it's absolutely true. You can't find the Big Bang's location because there isn't one. Here's why that makes sense. When space stretches, every point moves away from every other point at the same time. No single location controls this expansion. Imagine dots drawn on a balloon. As you blow up the balloon, every dot moves away from every other dot. From any dot's perspective, all the other dots are moving away from it. None of the dots represents the center of expansion. The expansion happens in the balloon's surface itself. Our universe works exactly like that balloon surface, except instead of a flat surface, it's three-dimensional space stretching in all directions. And instead of air inflating the balloon, it's the Big Bang continuously creating new space. Scientists measure the speed of distant star groups and find something remarkable. Double the distance to any star group, and you'll find it moving away twice as fast. This pattern holds true no matter where you position yourself in the universe. Every location sees itself as the center of expansion, which means the Big Bang happened everywhere at once. Look in any direction tonight. You'll see star groups moving away from you. Look the opposite direction. More star groups racing away. This creates a powerful illusion that you're sitting at the center of everything. Every conscious being in the universe experiences this exact same phenomenon. An alien on a planet millions of light years away would see their own night sky in exactly the same way. Star groups fleeing from their location in all directions. They'd also feel like the center of the universe. This uniform expansion reveals something profound about space itself. There's no special explosion site anywhere in the universe. No crater marking where the Big Bang happened. No center of expansion that scientists can point to with their telescopes. Astronomers call this the principle of the universe looking the same from everywhere. That's scientific terminology for no matter where you are, you see the same basic pattern of expansion. This principle became one of the foundations of modern space science. The expansion rate stays constant across the entire universe. Regions of space twice as far away from us move away twice as fast. This relationship holds true from every possible viewing point in the cosmos. The universe expands uniformly, making every location appear to be the center of the Big Bang. Most people assume space and time have always existed. They picture the Big Bang as an event that happened inside pre-existing space and time. This assumption misses the most mind-bending aspect of the universe's birth. Space and time themselves began with the Big Bang. Before this moment, before had no meaning. Distance had no meaning. Duration had no meaning. The Big Bang created the very framework that allows events to happen and objects to exist. Think of it like this. Every event in your life happens at some time and some place. You were born at a specific hospital on a specific date. You're listening to this at a specific location right now. But the Big Bang couldn't happen at a time or in a place because it created time and place. This concept breaks our everyday understanding of cause and effect. We're used to asking what happened before that. But asking what happened before the Big Bang is like asking what's north of the North Pole. The question itself doesn't make sense. Modern physics describes this beginning as a singularity. That's scientific terminology for a point where our normal understanding of space and time completely breaks down. At the moment of the Big Bang, space and time emerge from a condition that our minds can't fully grasp. When you measure how fast distant star groups move, you discover something that seems to put Earth at the center of everything. The farther away a group of stars, the faster it races away from us. This creates a convincing illusion of cosmic importance. This observation fooled scientists for decades. They wondered if Earth occupied some special position in the universe. Maybe we really were at the center of everything. Maybe the Big Bang happened right here in our cosmic neighborhood. The truth turned out to be far more elegant. These star groups aren't actually moving through space like cars on a highway. Space itself expands between them. It's the difference between cars driving away from you and the road itself stretching out in all directions. Scientists discovered this by studying light from distant star groups. When space stretches, it stretches the light waves traveling through it. This makes the light appear more red than it should. The more space between us and a star group, the more stretched and more red its light becomes. This stretching of space explains why distant star groups appear to flee from us at incredible speeds. They're not actually moving. They're being carried along as space itself grows larger. Every observer in the universe sees this same pattern, making the Big Bang a universal phenomenon rather than a local explosion. You cannot build a house without a foundation. You cannot have a conversation without language. You cannot have any event without space and time to contain it. The Big Bang created the foundation for everything that could ever happen. Most people think the Big Bang created matter and energy. That's only part of the story. The Big Bang also created the geometric structure of space itself. It created the flow of time. It created the basic framework that allows anything to exist anywhere at any moment. Before the Big Bang, the concepts of here and now had no meaning. There was no stage for matter to occupy. There was no timeline for events to unfold along. The Big Bang didn't just fill empty space with stuff. It created the very idea of space to be filled. Think of space as an invisible grid that stretches in all directions. This grid allows objects to have locations and distances between them. The Big Bang created this entire grid system from nothing. It also created time as a dimension that allows change and sequence to occur. Modern physics calls this the emergence of space-time. That's scientific terminology for the unified system of space and time that forms the foundation of reality. Without this space-time foundation, nothing we know could exist. Not stars, not planets, not even the simplest particles. What happened before the Big Bang? This question sounds perfectly reasonable. It's also completely meaningless. Here's why that's not just a clever word game. Time itself began with the Big Bang. Before this moment, there was no before. The word before only makes sense when time already exists. But time didn't exist until the Big Bang created as part of the fundamental structure of reality. Asking what happened before the Big Bang is like asking what's south of the South Pole. The question uses concepts that don't apply to the situation. There is no south once you reach the southernmost point on Earth. There was no before until time began. Scientists struggled with this concept for decades. They kept trying to imagine what conditions were like before the universe started. They eventually realized they were asking the wrong type of question entirely. The Big Bang marks the boundary of time itself. That's scientific terminology for the point where time begins and before which the concept of time has no meaning. This boundary represents the absolute limit of what we can ask about the past. Nothing preceded it because preceding requires time to already exist. Every law of physics stops working at the moment of the Big Bang. Every equation becomes meaningless. Every principle that explains how the universe operates breaks down completely. This reveals the most profound limitation in human knowledge. Scientists call this moment a singularity. That's scientific terminology for a point where the normal rules of physics no longer apply and our mathematical descriptions of reality fall apart. At this singular moment, temperature, density, and energy reach values that make no sense in normal physics. Imagine trying to use a map when you've walked off the edge of the world. Your map becomes useless because it was designed for places that actually exist. Physics equations become useless at the Big Bang because they were designed for conditions that follow normal rules. This breakdown isn't a failure of science. It's science discovering its own boundaries. The laws of physics describe how things behave after the universe already exists. They can't describe the moment when the universe comes into existence. Modern physics recognizes this is the point where we need entirely new theories. Current understanding hits a wall at the Big Bang singularity. Everything that makes the universe comprehensible to human minds simply stops working at this fundamental boundary. People often say the Big Bang started from a point smaller than an atom. This statement misses something crucial about the nature of the beginning. The Big Bang didn't start from something small. It started from a condition where size had no meaning at all. Size requires space to exist. You can only measure something as small or large when there's already a framework of space to measure it within. But space itself didn't exist until the Big Bang created it. Without space, the concept of size becomes meaningless. This isn't about something being extremely tiny. It's about the absence of the entire concept of dimension. Imagine trying to measure the length of happiness or the width of Tuesday. These measurements make no sense because length and width don't apply to emotions or days of the week. Physicists describe the Big Bang's beginning as a mathematical point. That's scientific terminology for a concept in mathematics that has no size, length, width, or height. It's pure location without dimension. This mathematical point isn't a tiny physical object. It's an abstract concept that represents the complete absence of spatial measurement. The Big Bang represents the moment when this dimensionless mathematical concept exploded into the three-dimensional space we experience today. Size itself came into existence along with space, making the question how big was it impossible to answer meaningfully. Modern physics cannot explain the Big Bang itself. This admission represents one of the most honest statements in all of science. The most fundamental event in the history of the universe lies beyond our current ability to understand. Every attempt to describe the Big Bang using current physics hits the same wall. Energy density becomes infinite. Temperature becomes infinite. The curvature of space becomes infinite. Infinite values break every equation and make every calculation impossible. Scientists need a theory that combines the physics of very large things with the physics of very small things. The physics of large things is called general relativity. The physics of small things is called quantum mechanics. These two theories contradict each other when applied to the Big Bang. Researchers are working on a unified theory called quantum gravity. That's scientific terminology for a theory that would explain how gravity works at the smallest possible scales where quantum mechanics dominates. This theory doesn't exist yet, but it might finally explain what really happened at the Big Bang. Until quantum gravity is developed, the Big Bang remains the greatest mystery in physics. It represents the point where human knowledge reaches its absolute limit and where the universe keeps its deepest secrets hidden from scientific understanding. Galaxies appear to race away from us at incredible speeds. This creates a powerful illusion. Most people assume these massive star collections are flying through empty space like cosmic bullets. They're not moving through space in that way. Space itself expands between galaxies. This carries them apart without much actual motion through space. It's the difference between cars driving away from each other and a road stretching longer while the cars sit still. Imagine ants walking on the surface of a balloon. If you inflate the balloon, the ants move apart from each other. But the ants aren't actually walking. The balloon's surface is expanding and carrying them along for the ride. This discovery overturned centuries of assumptions about cosmic motion. Astronomers realized that galaxies behave like passengers on an expanding cosmic highway. The highway itself grows larger, making the distance between passengers increase automatically. Scientists call this phenomenon cosmic expansion. That's scientific terminology for the continuous growth of space itself that increases distances between galaxies without any actual movement. This expansion explains why distant galaxies seem to flee from us at such tremendous speeds. They're being carried by expanding space. Draw dots on a deflated balloon with a marker. Now blow up the balloon slowly. Watch what happens to every single dot. Each dot moves away from every other dot at the same time. This balloon demonstration reveals the true nature of cosmic expansion. Space doesn't expand from one central point outward. It expands uniformly in all directions simultaneously. Every region of space stretches at the same rate as every other region. The balloon's surface represents our three-dimensional space compressed into 2 dimensions for easy visualization. Just as the balloon's surface has no center of expansion, our universe has no central location where expansion begins. This uniform expansion solves the mystery of why every galaxy appears to flee from our location. It's not because we occupy a special position. It's because expansion happens the same way everywhere in the universe. Astronomers measure this expansion and find remarkably close to uniformity. That's scientific terminology for the same rate of growth in all directions and all locations throughout the observable universe. This uniformity shows that space itself grows larger, rather than objects moving through pre-existing space. In the 1920s, an astronomer named Hubble made measurements that changed our understanding of the universe forever. He discovered a precise mathematical relationship between how far away a galaxy is and how fast it appears to be moving away from us. Double the distance to a galaxy, and you'll find it moving away twice as fast. Triple the distance, triple the speed. This relationship holds true for galaxies scattered across billions of light-years of space. This pattern would be impossible if galaxies were simply flying through static space. Random motion would create a chaotic mix of speeds and directions. Instead, Hubble found mathematical order throughout the cosmos. The relationship became known as Hubble's law. That's scientific terminology for the observation that a galaxy's recession speed is directly proportional to its distance from us. This law provides some of the strongest evidence that space itself expands uniformly. Hubble's law reveals that at a given cosmic time, the expansion rate looks consistent across space. Every million light-years of distance adds the same amount of recession speed. This mathematical precision strongly suggests that space expansion, not galaxy motion, explains what we observe in the night sky. Light waves get stretched as they travel through expanding space. This stretching changes the color of the light in a predictable way. The more space expands during a light wave's journey, the redder the light becomes when it reaches us. Scientists call this effect redshift. That's scientific terminology for the stretching of light waves by expanding space that makes them appear redder than when they were originally emitted. This stretching happens to all electromagnetic radiation traveling through space. The most dramatic example comes from the universe's oldest light. This ancient radiation was released when the universe was much younger and hotter. As space expanded over billions of years, this radiation got stretched from visible light into microwave radiation. Astronomers detect this ancient radiation coming from all directions in space. They call it the cosmic microwave background. That's scientific terminology for the stretched remains of the first light that could travel freely through the early universe. The temperature of this background radiation decreases as the universe expands. Space expansion stretches the radiation's wavelengths, making it cooler and redder. This cooling effect provides direct evidence that space has been expanding for billions of years, carrying ancient light along for the journey. Space expands everywhere in the universe, but you don't notice this expansion in your daily life. Your body doesn't stretch. Buildings don't grow larger. The distance between Earth and the Sun remains constant. Gravity prevents expansion on small scales. Within our galaxy, gravity holds everything together much more strongly than space expansion tries to pull things apart. The same applies to our local group of nearby galaxies. Gravity wins the battle against expansion in these small cosmic neighborhoods. Scientists call these gravitationally bound structures. That's scientific terminology for collections of matter held together by gravity that are strong enough to resist the effects of cosmic expansion. These structures maintain their size while space expands around them. Galaxy clusters represent the largest structures where gravity can overpower expansion. These massive collections contain hundreds or thousands of galaxies held together by their combined gravitational pull. Only on the largest scales does space expansion dominate over gravity. Between galaxy clusters, space stretches freely and carries these massive structures apart. This creates a cosmic hierarchy where gravity controls small scales and expansion controls the largest scales in the universe. Why does the universe look basically the same in every direction? This question puzzled scientists for centuries. The answer reveals something profound about the nature of space itself. Look up at the night sky from anywhere on Earth. You'll see roughly the same number of stars scattered in roughly the same patterns. Travel to another galaxy millions of light years away. You'd see essentially the same type of cosmic neighborhood surrounding you. This uniformity extends far beyond what our eyes can see. When astronomers map the locations of galaxies across vast regions of space, they find an amazing pattern. The density of matter stays remarkably consistent throughout the observable universe. Scientists call this large-scale homogeneity. That's scientific terminology for the even distribution of matter and energy when you look at sufficiently large regions of the universe. This homogeneity appears at scales of hundreds of millions of light years. The universe maintains this uniform density despite containing over 100 billion galaxies scattered across mind-boggling distances. No single region appears denser or emptier than any other region when viewed from this cosmic perspective. This consistency suggests that no location in the universe occupies a special or central position. You cannot find a single hot spot or cold spot in the universe's most ancient light. This uniform temperature exists in every direction you look. The consistency is so perfect it seems almost impossible. This ancient light comes from a time when the universe was much younger and hotter. Scientists call it the cosmic microwave background radiation. That's scientific terminology for leftover heat from the early universe that now fills all of space uniformly. Satellites measure this background radiation with incredible precision. They find the same temperature in every direction to within tiny fractions of a degree. The northern sky shows the same temperature as the southern sky. The eastern horizon matches the western horizon perfectly. This temperature uniformity spans regions of space that could never have communicated with each other. Light from opposite sides of the sky would have needed more time to travel between them than the universe has existed. The perfect temperature balance reveals that the early universe was already uniform when this ancient light was first released. This uniformity has been preserved across billions of years of cosmic expansion, providing direct evidence that the universe lacks any preferred center or direction. Up close, the universe looks incredibly lumpy and uneven. Galaxies cluster together in dense groups. Vast empty regions stretch between these clusters. Matter appears to clump in a chaotic, random pattern throughout space. Step back to view much larger scales. Something remarkable happens to this apparent chaos. The clumps and empty regions average out into a smooth, even distribution. The universe transforms from lumpy to uniform when viewed from the proper distance. Imagine looking at a brick wall from inches away. You'd see individual bricks, mortar gaps, and surface textures. Step back several yards. The wall appears smooth and uniform despite being made of separate components. Astronomers map galaxy locations across billions of light years of space. At these enormous scales, they find perfect evenness. Regions containing many galaxy clusters balance out regions with few clusters. The average density stays constant everywhere. This smoothing effect occurs at scales larger than 300 million light years. That's scientific terminology for the distance scale above which the universe's lumpiness averages out into perfect uniformity. Below this scale, structure dominates. Above this scale, smoothness prevails throughout the observable universe. This discovery eliminated our privileged position in the universe forever. Scientists realized that every observer, no matter where they're located, would see the same basic cosmic phenomena. Earth occupies no special vantage point in space. The principle emerged from centuries of scientific humility. First, Earth was removed from the center of the solar system. Then, our solar system lost its central position in the galaxy. Finally, even our galaxy lost its special status in the universe. Astronomers call this the Copernican principle applied to cosmology. That's scientific terminology for the assumption that humans do not occupy a special or central position in the universe. This principle revolutionized our understanding of cosmic structure. Any alien civilization in any distant galaxy would observe the same expansion pattern we see. They'd find galaxies receding from their location at speeds proportional to distance. They detect the same background radiation temperature in all directions. The Copernican principle means that cosmic phenomena don't depend on the observer's location. Universal laws operate the same way everywhere in space. No matter where you position yourself in the universe, you'd witness identical evidence for the Big Bang's effects on cosmic structure and expansion. Every measurement confirms the same pattern throughout the observable universe. No direction appears special. No location claims central importance. No observer can legitimately argue they occupy the universe's center. Scientists combined all these observations into a single powerful principle. When the universe shows the same properties in all directions, astronomers call it isotropic. When it shows the same density everywhere, they call it homogeneous. The cosmological principle states that the universe is both isotropic and homogeneous on large scales. That scientific terminology for the universe looks the same in all directions and has the same density everywhere when viewed from any location. This principle makes the Big Bang's lack of location inevitable. If every point in space appears to be at the center of expansion, then no point can actually be the center. The Big Bang happened everywhere simultaneously because everywhere is equivalent. The cosmological principle became the foundation of modern understanding about the universe's structure and history. It confirms that the Big Bang created space uniformly in all directions, making every location equally valid as the apparent center of cosmic expansion throughout the observable universe. No observer in the universe can claim a more important position than any other observer. This principle revolutionized our understanding of cosmic structure. It means your location has no special significance compared to locations billions of light years away. Scientists established this rule after centuries of careful observation. They found that basic cosmic phenomena appear identical regardless of where you position yourself in the universe. The expansion rate looks the same. The background radiation shows the same temperature. Galaxy distributions follow the same patterns. This observer equality applies to every conscious being throughout the cosmos. An alien scientist in a distant galaxy would measure identical cosmic expansion rates. They'd detect the same background radiation temperature. They'd observe the same relationship between galaxy distance and recession speed. The principle emerged from combining two key observations. The universe appears uniform when you look in any direction from your location. The universe also shows the same density of matter when you sample large enough regions of space. Scientists call this the cosmological principle. That's scientific terminology for the assumption that the universe has the same basic properties when observed from any location and in any direction. This principle eliminates the possibility that any location, including Earth, occupies a privileged position in cosmic structure. Apply the cosmological principle perfectly, and something remarkable happens to the possible shapes of space itself. The universe can only have three different geometric forms. No other possibilities exist in mathematics. Space can be flat like a tabletop, extending infinitely in all directions. In this geometry, parallel lines never meet. The angles of triangles always add up to exactly 180 degrees. Light travels in perfectly straight lines across vast distances. Space can be curved like the surface of a sphere. In this geometry, parallel lines eventually meet at poles. Triangle angles add up to more than 180 degrees. Light traveling in straight lines eventually returns to its starting point. Space can be curved like a saddle, extending infinitely in all directions. In this geometry, parallel lines spread apart forever. Triangle angles add up to less than 180 degrees. Light rays that start parallel diverge continuously. These represent the only three possible geometries for uniform space. That's scientific terminology for the complete set of mathematical solutions for space that looks the same in all directions and at all locations. The cosmological principle forces space into one of these three geometric forms throughout the observable universe. Here's a crucial insight about cosmic time. The universe can change dramatically over billions of years while still maintaining perfect equality between all observers. Time evolution doesn't violate the cosmological principle. Imagine taking a snapshot of the entire universe at any single moment in cosmic history. Every location would show identical conditions at that specific time. Galaxies everywhere would have the same average density. Space would expand at the same rate in all regions. Wait a billion years and take another cosmic snapshot. Conditions everywhere would have changed in exactly the same way. Galaxies would be more spread out by the same amount. Stars would have aged by identical amounts. The background radiation would have cooled uniformly. This temporal uniformity allows the universe to evolve while preserving its democratic nature. Every location experiences the same cosmic history. No region ages faster or slower than any other region across vast scales of space. Scientists call this temporal homogeneity. That's scientific terminology for the property that all locations in the universe experience identical changes over time when viewed on large scales. This temporal equality ensures that cosmic evolution proceeds uniformly throughout space, maintaining the cosmological principle across billions of years of universal history. Decades of astronomical measurements support the cosmological principle with remarkable precision. Every major observation aligns with the prediction that no location occupies a special position in space. The evidence spans multiple independent lines of research. Galaxy surveys map the positions of millions of star clusters across billions of light years. These surveys find uniform density when averaged over sufficiently large regions. No direction shows higher galaxy concentrations. No region appears systematically emptier than others. Background radiation measurements detect the same temperature in every direction with incredible accuracy. Satellites mapping this ancient light find perfect isotropy across the entire sky. Temperature variations remain smaller than 1 part in 100,000 throughout all directions. Supernova observations measure cosmic expansion from multiple viewing angles across the sky. These measurements confirm that expansion appears identical regardless of which direction astronomers point their telescopes. Distance-velocity relationships remain constant in all directions. The observational verification establishes the cosmological principle as a fundamental feature of our universe. That's scientific terminology for the process by which multiple independent measurements confirm that the universe actually does exhibit the uniform properties predicted by the principle. This verification provides the observational foundation for modern cosmological theories about the Big Bang's universal nature. The cosmological principle only works at enormously large scales in the universe. Look too closely, and the principle falls apart completely. Perfect uniformity exists only when you step back far enough to average out local irregularities. Within our galaxy, matter clumps dramatically around stars and planets. Our solar system contains vastly more matter per cubic meter than the empty space between stars. These local concentrations violate uniformity on small scales. Galaxy clusters contain hundreds of individual galaxies packed into relatively small regions of space. Between clusters, vast voids stretch for millions of light years with almost no galaxies at all. This clustering creates huge variations in local density. The principle begins to apply only above scales of several 100 million light years. Below this threshold, local structure dominates over cosmic uniformity. Above this threshold, uniformity dominates over local structure throughout observable space. Scientists call this the scale of homogeneity. That's scientific terminology for the minimum distance scale above which the universe appears uniform and below which local structures create significant density variations. This scale limitation means the cosmological principle describes the universe's large-scale architecture while allowing rich structure formation on smaller scales. Light travels fast, but not infinitely fast. This speed limit creates an invisible boundary around every observer in the universe. Beyond this boundary, no information can ever reach you, no matter how long you wait. The universe has existed for a finite amount of time since the Big Bang. Light from distant objects needs time to travel through space before reaching your eyes. Objects too far away simply haven't had enough time to send their light to your location yet. This creates what scientists call the observable universe. That's scientific terminology for the spherical region of space from which light has had enough time to reach a particular observer since the universe began. This sphere surrounds every conscious being throughout the cosmos. Imagine standing in the middle of a giant sphere made of invisible walls. Light from objects inside the sphere can reach you. Light from objects beyond the sphere cannot reach you because the universe hasn't existed long enough for that light to complete its journey. The boundary of this sphere moves outward constantly as the universe ages. Every second that passes allows light from slightly more distant objects to reach you. But this boundary always exists, creating a fundamental limit on what any observer can ever see or detect in the universe. Measure the size of the observable universe, and you'll find something that seems impossible at first. The boundary extends much farther than light could have traveled since the Big Bang. This apparent contradiction reveals a crucial feature of cosmic expansion. Light from the most distant observable objects has been traveling toward us for nearly the entire age of the universe. You might expect these objects to be located at a distance equal to the speed of light multiplied by the universe's age. They're actually much farther away. Here's why this happens. When distant light began its journey toward us, space was much smaller than it is today. The light started from a location that was relatively close to our cosmic neighborhood, but space expanded dramatically while the light was traveling. The object that emitted the light got carried farther away as space expanded around it. By the time its light reaches us today, the object sits at a much greater distance than when it first sent out that light toward our location. Scientists measure the current distance to the most remote observable objects at about 46 billion light-years away. That's scientific terminology for the actual present-day distance to objects whose light has been traveling toward us for nearly 14 billion years. Space expansion stretched these distances far beyond what simple light travel time would suggest. Every conscious being in the universe lives at the center of their own personal observable universe. These individual spheres of visibility don't match up perfectly between different observers. Each observer sees a unique portion of the total cosmos. An alien living in a galaxy billions of light years away would have their own observable universe centered on their location. The boundary of their observable sphere would be completely different from the boundary of your observable sphere. Some regions visible to them would be invisible to you. The overlap between different observers' universes depends on how far apart they're located. Observers close to each other see mostly the same cosmic neighborhood. Observers extremely far apart might have observable universes that barely overlap at all. This means the total universe extends far beyond what any single observer can ever detect. Your personal observable universe represents just one small window into a much larger cosmic reality that spans distances beyond individual observation limits. The concept of multiple observation horizons reveals that no single observer can claim to see the entire universe. That's scientific terminology for the recognition that each observer's view is limited to their own spherical region, and the total cosmos extends far beyond any individual's detection capabilities. Every observer experiences their own limited but complete view of cosmic structure and history. Regions of space exist that you can never observe, measure, or detect through any possible method. These areas lie beyond your observation horizon and will remain forever invisible to you. They exist, but they're completely inaccessible to your scientific instruments. These unobservable regions follow the same physical laws as the parts of the universe you can see. Gravity works the same way there. Stars form and evolve according to identical processes. Galaxies cluster and separate following the same rules that govern observable cosmic structure. The physical properties of unobservable space don't change just because you can't see them. Matter has the same density. Space expands at the same rate. The background radiation maintains the same temperature throughout both observable and unobservable regions. Scientists cannot directly study these invisible areas, but they can infer their properties from the observable universe. If the cosmos appears uniform in all directions that can be seen, it probably continues uniformly in directions that cannot be seen. The existence of unobservable regions means the total universe might be infinite in size. That's scientific terminology for the possibility that space extends forever beyond the observable boundary, containing unlimited amounts of matter and energy following the same laws as the detectable cosmos. These invisible regions represent the ultimate limit of human knowledge about the universe's true scope and contents. Two competing forces determine whether more of the universe becomes visible to you over time. Light constantly arrives from more distant objects as the universe ages, but cosmic expansion accelerates and carries distant objects away faster than light can travel between them. In the early universe, the first force was winning. Every moment that passed brought light from more distant objects into view. The observable universe grew steadily larger as more regions became detectable for the first time. Recent discoveries show that cosmic expansion is accelerating due to a mysterious force called dark energy. This acceleration means that very distant objects are moving away from us faster than the speed of light due to space expansion between us and them. The acceleration creates a cosmic horizon beyond which objects are receding so fast that their light can never reach us, even given infinite time. Objects beyond this horizon become permanently invisible, no matter how long we wait for their light to arrive. Scientists call this the ultimate limit of cosmic visibility. That's scientific terminology for the maximum distance from which light can ever reach an observer, determined by the balance between light travel time and the acceleration of cosmic expansion. This limit means there is a maximum to what can ever become visible in principle, and over time some distant objects can disappear from view permanently. The universe shows near-perfect temperature uniformity in every direction you look. This uniformity should be completely impossible. The distances involved are simply too vast for any heat-balancing process to work across the entire cosmos. Scientists measure the ancient background radiation that fills all of space. This radiation comes from regions of the early universe that were separated by enormous distances. These regions could never have communicated with each other to coordinate their temperatures. Think of two ovens in separate buildings on opposite sides of a large city. You'd never expect them to heat up to exactly the same temperature without some way to share heat between them. Yet regions of the early universe achieved near-perfect temperature balance despite being much farther apart than these ovens. The background radiation shows the same temperature to within tiny fractions of a degree across the entire sky. Regions in the north show identical temperatures to regions in the south. Eastern sectors match western sectors with incredible precision. This temperature uniformity reveals a fundamental puzzle about the early universe. That's scientific terminology for the problem of explaining how widely separated regions achieved identical conditions without any physical mechanism to coordinate them. The near perfection of this temperature balance across impossible distances created one of cosmology's greatest mysteries. Physical processes cannot operate faster than the speed of light. This speed limit makes it impossible for distant regions of the universe to share heat or coordinate their temperatures. Yet near-perfect thermal equilibrium exists across regions that should never have been able to communicate. 2. Heat flows from warm objects to cooler objects until they reach the same temperature. This process requires some form of contact or connection between the objects involved. Without contact, temperature differences persist indefinitely between separate systems. Light represents the fastest possible way for regions of space to exchange information or energy. But even light cannot travel fast enough to connect the most distant, visible regions of the early universe. These regions remain completely isolated from each other. Calculate the time required for light to travel between opposite sides of the observable universe. The result shows that these regions could never have exchanged heat during the time available since the Big Bang began. They should show completely different temperatures today. The existence of thermal equilibrium across causally disconnected regions violates everything scientists understand about heat transfer. That's scientific terminology for the achievement of identical temperatures between regions that cannot physically interact or exchange energy. This equilibrium should be impossible according to basic physics, yet it exists throughout the observable universe. Consider this puzzle. Regions of the universe that could never have influenced each other show identical properties. They have the same density, the same temperature, and the same rate of expansion. This coordination appears to violate the principle of causality itself. Causality requires that effects follow causes through physical connections. One region can only influence another region if signals or forces can travel between them within the available time. The speed of light limits how quickly any influence can spread across space. Map the regions of the early universe that could have communicated with each other through light signals. These causally connected patches turn out to be much smaller than the uniform regions we actually observe today. Each patch should have developed different properties in isolation. Instead, the universe shows uniformity across scales far larger than causality allows. Temperature, density, and expansion rate remain constant across regions separated by distances that light could never have crossed in the available time. This coordination without communication suggests something unnatural about the universe's initial conditions. That's scientific terminology for the requirement that the Big Bang began with precisely identical conditions in regions that had no physical way to coordinate with each other. This fine-tuning seems to require an extraordinary coincidence that scientists find deeply unsatisfying. Calculate the maximum distance that light could have traveled by the time the background radiation was released. This calculation reveals a shocking mismatch between theoretical expectations and actual observations. The uniform regions are far larger than physics allows. Scientists call this maximum distance the horizon size at the time of radiation release. That's scientific terminology for the diameter of the largest region that could have been causally connected when the cosmic background radiation was first emitted. This represents the biggest patch that could have achieved thermal equilibrium. The horizon size calculation gives a result of about 2 degrees when viewed from our current location. This means the background radiations should show different temperatures in regions separated by more than 2 degrees across the sky. Thermal equilibrium could not extend beyond this limit. Actual observations show near-perfect temperature uniformity across the entire 360-degree sky. The uniform region is roughly 180 times larger than the maximum size that causality allows. This represents an enormous discrepancy between theory and measurement. The size mismatch reveals that standard Big Bang theory cannot explain the universe we actually observe. The theory predicts a patchy, uneven cosmos with dramatic temperature variations across the sky. Reality shows near-perfect smoothness across scales that should have been impossible to coordinate through any known physical process. Standard Big Bang theory fails to solve the horizon problem through any known mechanism. This failure forces scientists to admit that something crucial is missing from our understanding of the early universe. New physics must be involved in creating the uniformity we observe. The theory correctly predicts many features of the observable universe. It explains cosmic expansion, element abundances, and the existence of background radiation. But it cannot account for the near perfection of this radiation's temperature uniformity across impossible distances. Scientists have tried numerous modifications to standard theory. They've adjusted initial conditions, modified expansion rates, and proposed exotic forms of matter. None of these approaches successfully explains how causally disconnected regions achieved near-perfect coordination. The horizon problem reveals a fundamental gap in cosmological theory. Every attempt to solve it using conventional physics runs into the same barrier. The speed of light simply does not allow enough time for thermal equilibrium to develop across the observed scales. This theoretical crisis led to the recognition that the early universe required special mechanisms beyond standard Big Bang physics. That's scientific terminology for the realization that conventional expansion cannot explain observed uniformity, and that revolutionary new processes must have operated during the universe's first moments. This recognition opened the door to entirely new theories about how the cosmos began and evolved to its current state. Scientists proposed a radical solution to the horizon problem. What if the early universe underwent a period of incredibly rapid expansion? This expansion could stretch a small, uniform region to cover the vast distances we observe today. Imagine a tiny patch of space where all regions could easily communicate and share heat. This patch starts smaller than an atom but contains enough material to eventually become the entire observable universe. Every part of this patch reaches the same temperature before expansion begins. Now imagine this patch suddenly inflating faster than anything in normal physics. Space itself expands at an exponential rate, carrying the uniform conditions throughout the growing region. The patch grows from subatomic size to cosmic scale in an incredibly brief moment. This rapid expansion preserves the original uniformity across the newly created vast distances. Regions that started in thermal contact remain at the same temperature, even after being separated by billions of light years. The initial communication creates permanent coordination. Scientists call this process cosmic inflation. That's scientific terminology for a period of exponential expansion in the early universe that stretched small, causally connected regions to cover the entire observable cosmos. This inflation explains how perfect uniformity could exist across distances that normal expansion could never coordinate. A special energy field must have powered the inflationary expansion of space. This field provided the enormous energy needed to stretch space faster than light could travel across it. The field behaved unlike any form of matter or energy we observe today. Normal matter and energy become less dense as space expands around them. Pour water into an expanding balloon, and the water gets more diluted as the balloon grows larger. But the inflation field maintained constant energy density even as space stretched exponentially. This constant energy density created a repulsive gravitational effect. Einstein's equations show that energy with constant density generates antigravity rather than normal attractive gravity. This antigravity drove space to expand exponentially fast. The field existed in what physicists call a false vacuum state. That's scientific terminology for a temporary energy configuration that appears stable but will eventually decay to a lower energy state. This unstable condition provided the energy source for cosmic inflation. Eventually, the inflation field decayed from its high energy state to a lower energy configuration. This decay ended the inflationary period and released enormous amounts of energy that heated the universe and created the hot, dense conditions of the traditional Big Bang scenario. During inflation, quantum mechanics operated on the smallest possible scales within the rapidly expanding space. Tiny random fluctuations appeared and disappeared continuously throughout the inflating region. These fluctuations normally remain invisible at the quantum level. The exponential expansion of space stretched these microscopic quantum fluctuations to astronomical sizes. What began as undetectable variations in energy density became the seeds of all cosmic structure. Mountains and valleys in the quantum realm transformed into the blueprints for galaxies and galaxy clusters. This amplification process worked like a cosmic photocopier, enlarging a microscopic image. The original quantum variations contained random patterns of slightly higher and lower energy density. Inflation expanded these patterns while preserving their relative strength and distribution. The amplified fluctuations created the first non-uniform regions in an otherwise perfectly smooth universe. These slight density variations provided the gravitational seeds around which matter could later clump together to form stars, galaxies, and larger cosmic structures. Scientists observe the signatures of these ancient quantum fluctuations in today's cosmic microwave background radiation. That's scientific terminology for the leftover radiation from the early universe that still shows tiny temperature variations corresponding to the original quantum fluctuations amplified by inflation. These variations prove that quantum mechanics operated during the inflationary period. Inflation had to end for the normal Big Bang universe to begin. The decay of the inflation field triggered a dramatic transformation that filled space with the hot, dense matter and radiation we associate with the early cosmos. This transformation connected inflation to traditional Big Bang physics. The inflation field contained enormous amounts of energy stored in its unstable configuration. When this field finally decayed, it released all of this stored energy into ordinary particles and radiation. Space filled with extremely hot matter for the first time since inflation began. This energy release process is called reheating. That's scientific terminology for the conversion of inflation field energy into the hot, dense collection of particles and radiation that characterized the early Big Bang universe. Reheating marked the end of the inflationary period. The temperature after reheating was incredibly high, but much lower than the energy scale of inflation itself. The universe emerged from inflation filled with fundamental particles like quarks, electrons, and photons. These particles behaved according to the normal physics of hot, dense matter. Reheating created the initial conditions for all subsequent cosmic evolution. The hot, dense universe that emerged from reheating underwent normal expansion and cooling, leading to element formation, structure growth, and eventually the formation of stars, galaxies, and planets throughout cosmic history. Inflation simultaneously solved another major cosmic puzzle. Observations show that space appears to be perfectly flat on large scales. This flatness seemed to require incredibly precise initial conditions in the early universe. Inflation explains this flatness naturally through extreme stretching. Space can have different geometric properties depending on its curvature. It can curve like the surface of a sphere, bend like a saddle, or remain flat like a tabletop. Each type of curvature creates different behaviors for light rays and geometric shapes. Before inflation, space could have had any amount of curvature. It might have been highly curved in complex ways throughout different regions. The total geometry could have been far from the flat configuration we observe today. Exponential expansion flattened any initial curvature through sheer stretching. Imagine drawing a small circle on a balloon, then inflating the balloon to enormous size. The circle's edge becomes so flat that it appears straight. Similarly, inflation stretched space until any original curvature became undetectable. The inflationary stretching explains why space appears flat without requiring special initial conditions. That's scientific terminology for the process by which exponential expansion naturally produces flat geometry regardless of the original curvature of space. This geometric flattening represents another successful prediction of inflation theory that matches observations of our universe's structure. Draw a triangle on a flat piece of paper. Measure the angles at each corner. Add them together. You'll get exactly 180 degrees every single time. This simple result reveals the fundamental nature of flat geometry. Flat space follows the rules you learned in school mathematics. Parallel lines never meet, no matter how far you extend them. The shortest distance between 2 points is always a straight line. Circles have the same ratio of circumference to diameter everywhere. If our universe has flat geometry, then these familiar rules apply on the largest possible scales. Light travels in perfectly straight lines across billions of light years. Parallel laser beams shot in the same direction would never converge or diverge from each other. Flat geometry means space extends infinitely in all directions without any curvature or bending. There are no edges, boundaries, or special locations where the rules change. Every region of space behaves identically to every other region throughout the infinite expanse. Scientists call this Euclidean geometry applied to cosmology. That's scientific terminology for the familiar flat geometry from mathematics extended to describe the shape of space throughout the entire universe. In a flat universe, space continues forever without any curvature, making infinite size the most natural possibility. Launch a spaceship in any direction from Earth. Keep traveling in that exact same direction for long enough. In a spherical universe, you would eventually return to Earth from the opposite direction. The universe would be finite, but have no edges or boundaries. This happens because space itself curves back on itself like the surface of a sphere. Just as you can walk around the Earth's surface and return to your starting point, you could travel through a spherical universe and complete a cosmic loop. The total volume of a spherical universe would be enormous but limited. You could theoretically count every atom in existence because the total amount of space would be finite. There would be a specific number of galaxies and a maximum distance between any 2 points. In spherical geometry, parallel lines eventually meet at cosmic poles, but triangles drawn on large enough scales would have angles that add up to more than 180 degrees. Light beams traveling in the same direction would slowly converge and eventually cross each other. This type of universe represents a closed cosmic geometry. That's scientific terminology for a finite universe where space curves back on itself, creating a bounded cosmos with no edges or special boundary conditions. A spherical universe would contain all of existence within a vast but limited volume of curved space. Imagine space curved like a saddle extending infinitely in all directions. In this geometry, parallel lines don't stay parallel. They spread farther and farther apart as they extend into the distance. This creates a universe that expands in ways that go beyond simple size growth. Hyperbolic space has negative curvature throughout its entire structure. This means that triangles drawn on large scales have angles that add up to less than 180 degrees. The deficit becomes more pronounced as you draw larger and larger triangles across cosmic distances. Light beams that start parallel in hyperbolic space diverge continuously. They spread apart faster than they would in flat space. This creates optical effects that would make distant objects appear smaller and dimmer than expected from their actual size and brightness. A hyperbolic universe would be infinite in size and contain unlimited amounts of matter and energy. The negative curvature would cause space to expand more rapidly than in flat geometry. This accelerated expansion would affect the evolution and structure of cosmic architecture. Scientists call this an open universe with saddle geometry. That's scientific terminology for an infinite cosmos where space has negative curvature, causing parallel lines to diverge and triangles to have angle sums less than 180 degrees. This geometry creates a universe that expands both in size and in its rate of expansion throughout cosmic time. Satellites measuring the cosmic microwave background radiation have determined the curvature of space with incredible precision. These measurements represent some of the most accurate observations in the history of astronomy. The results point to a universe that appears virtually flat. The measurements work by analyzing the size of temperature fluctuations in the ancient background radiation. Different geometries would create different patterns in these fluctuations. Spherical space would make the patterns appear larger. Hyperbolic space would make them appear smaller. Observations show that the patterns match the predictions of flat geometry to within a fraction of 1%. The universe appears to be flat to within measurement uncertainty. Any curvature that exists must be incredibly small and undetectable with current instruments. These results suggest that space extends essentially infinitely in all directions. The cosmos appears to follow Euclidean geometry on the largest observable scales. Parallel lines remain parallel, and triangles have angles that sum to 180 degrees throughout the visible universe. The near-perfect flatness observed in cosmic geometry supports theories of inflation that naturally produce flat space. That's scientific terminology for the measurement results showing that universal geometry matches flat space within observational errors, supporting theoretical models that predict geometric flatness. This flatness implies an infinite cosmos extending far beyond the observable boundary. We can only observe a tiny fraction of the total universe that may exist. This observational limitation creates a fundamental problem in determining the true properties of the entire cosmos. Our conclusions about universal geometry may apply only to the small region we can actually see. The observable universe represents just one small patch within what might be an infinite expanse of space. Drawing conclusions about the whole universe from this limited sample is like trying to determine the shape of an entire ocean by examining one drop of water. Even if space appears flat throughout the observable region, it could have different curvature in distant areas beyond our detection limits. The universe might curve in complex ways that become apparent only on scales much larger than we can observe. The total universe could be finite or infinite in size. It could have uniform curvature or variable geometry in different regions. Current observations cannot distinguish between these possibilities because they're limited to our local cosmic neighborhood. This represents the ultimate boundary of cosmological knowledge about universal structure. That's scientific terminology for the fundamental limit on what we can determine about the entire universe based on observations restricted to the small region of space from which light has had time to reach us. The true nature of the complete cosmos remains one of the deepest mysteries in science. Space could be twisted into shapes that seem impossible to imagine. Scientists have discovered that the universe might have the same curvature everywhere, while still being shaped like a donut, a pretzel, or even more bizarre configurations. Geometry and shape represent completely different aspects of cosmic architecture. Think of different ways to shape a piece of paper without changing its essential flatness. You can roll it into a cylinder, twist it into a Mobius strip, or connect the edges to form complex surfaces. The paper remains flat locally, but its global shape becomes dramatically different. The universe could follow this same principle on cosmic scales. Space might be flat everywhere you look while still being connected in strange ways across vast distances. You could travel in what seems like a straight line and eventually return to your starting point from an unexpected direction. These exotic shapes create observable signatures that scientists can search for. Light from distant galaxies might show multiple images of the same objects viewed from different angles. The cosmic microwave background might display repeating patterns that reveal the universe's hidden connections. Scientists call this cosmic topology. That's scientific terminology for the study of how space might be connected in complex ways even when it appears to have simple geometry everywhere locally. This topology research reveals that the universe's true shape might be far stranger than its apparent flatness suggests. What if our entire observable universe represents just one bubble in an infinite sea of cosmic bubbles? This possibility emerged from theories that extend beyond our single Big Bang event. Our cosmic explosion might be happening alongside countless other explosions throughout a much larger reality. Inflation theory suggests that the rapid expansion creating our universe might continue forever in other regions of a vast cosmic landscape. While inflation ended in our local region and created our Big Bang, it could persist elsewhere and trigger additional Big Bang events continuously. Each of these separate Big Bang events would create its own independent universe with its own space, time, and physical laws. These pocket universes would exist in parallel but remain completely isolated from each other. No communication or travel between them would be possible. Our Big Bang's location becomes meaningless in this larger context. Instead of asking where our Big Bang happened, we should ask where our cosmic bubble sits within the infinite multiverse structure. Our entire reality becomes just one small region in an endless collection of universes. This multiverse concept reframes the Big Bang location problem completely. That's scientific terminology for the theoretical framework where our universe represents just one of many cosmic regions created by ongoing inflation in a vast, eternal cosmic structure. In this context, our Big Bang happened everywhere within our bubble while being nowhere special in the larger multiverse. Current physics breaks down completely at the moment of the Big Bang itself. Scientists are developing new theories that combine the physics of very large things with the physics of very small things. These theories might finally explain what really happened when space and time began. The problem comes from trying to apply both general relativity and quantum mechanics to the same extreme conditions. General relativity describes gravity and large-scale space. Quantum mechanics describes the behavior of particles at the smallest scales. These two theories contradict each other when applied to the Big Bang. Quantum gravity represents the attempt to create a unified theory that works at all scales. This new physics would describe how space and time behave when they're compressed to quantum dimensions. It might reveal that the Big Bang singularity doesn't actually exist. Instead of a true beginning, quantum gravity might show that space and time emerged from a more fundamental quantum state. The Big Bang could represent a transition between different phases of reality rather than the absolute start of existence. These quantum gravity theories could revolutionize our understanding of cosmic origins. That's scientific terminology for the potential new physics that would describe gravity at quantum scales and might eliminate the concept of a Big Bang singularity entirely. This revolution could reveal that asking about the Big Bang's location involves completely wrong assumptions about the nature of space, time, and cosmic beginnings. Scientists have discovered that most of the universe consists of invisible components that don't interact with light. These dark components might force major revisions to our understanding of how the universe expanded from the Big Bang. Their true nature remains one of cosmology's greatest unsolved mysteries. Dark matter outweighs all visible matter by a ratio of roughly 5:1. This invisible matter affects galaxy rotation and cosmic structure formation, but scientists don't know what particles create it. Dark matter could represent completely unknown physics beyond current theories. Dark energy dominates the universe even more dramatically than dark matter. This mysterious force drives the acceleration of cosmic expansion and represents about 70% of all energy in the cosmos. no current theory adequately explains what dark energy actually is. Understanding these dark components could change the entire story of cosmic expansion. If dark matter behaves differently than expected, it might affect how structure formed after the Big Bang. If dark energy evolved over time, it could alter the expansion history of space itself. Future discoveries about dark matter and dark energy might require completely new models of cosmic evolution. That's scientific terminology for the potential revolution in cosmology that could result from determining the true nature of the invisible components that dominate universal composition. These discoveries could reveal that our current understanding of Big Bang expansion represents only a small part of a much more complex cosmic story. New telescopes and detection methods will soon observe the universe's earliest moments with unprecedented precision. These advanced instruments might provide direct evidence for inflation theory and reveal new insights about the Big Bang's true nature. The next generation of cosmic archaeology will push observational boundaries beyond current limits. Space-based telescopes will detect gravitational waves from the inflationary period itself. These ripples in space would provide the first direct evidence that rapid expansion actually occurred in the early universe. The waves would carry information about conditions during inflation that no other method can access. Advanced surveys will map the three-dimensional structure of matter across billions of light years with incredible detail. These maps will reveal how cosmic architecture evolved from the earliest quantum fluctuations to today's galaxy clusters. The data will test inflation theory's predictions about structure formation. Precision measurements of the cosmic microwave background will continue improving with new satellite missions. These observations might detect signatures of quantum gravity effects or evidence for multiverse interactions that occurred during the Big Bang period. The combination of gravitational wave detection, structure mapping, and background radiation analysis will create the most complete picture of cosmic origins ever assembled. That's scientific terminology for the Coordinated Observational Program, using multiple advanced technologies to study the universe's earliest moments and test fundamental theories about cosmic beginnings. These observations will either confirm current Big Bang theories or force scientists to develop entirely new explanations for how the universe began and evolved to its present state.